Question 9. The table gives information about the scores achieved by students in a French test and in a German test. The scores in each test are modeled by a normal distribution. Here's the data, and on the grid we need to sketch a diagram for each of the distribution of scores and label each of them. So let's just highlight what we know. A normal distribution is something you must be familiar with, not in too much detail, however you still need to know the key characteristics. And then we just need to sketch, which means you don't have to be plain accurate, but it needs to have the general gist. Therefore you need to be able to show some differences between the two. So let's quickly look at the key characteristics of a normal distribution. So if we just have this here, we have this sign is marked as the mean, and this is the peak of a bell-shaped curve, and that is one key feature, is that it is bell-shaped. And then you need to also learn that there are different levels of standard deviations. You can have 1 standard deviation, 2 standard deviations, and 3 standard deviations, and all of them come with a plus or minus, and that indicates that it is plus or minus from the mean. So you could have the mean plus or minus 1, 2, or 3 standard deviations. And then there's the empirical rule with the 67 or 68 formula. You just need to look at that and revise that. However, right now you don't really need to think about it too much in detail. We're given the standard deviation and the means, so we can start by looking at just the French. The French has a mean score of 78, and it's got a standard deviation of 2. Now, pretty much 99% of the data, or somewhere thereabouts, is within 3 standard deviations each side of the mean. So anything outside 3 standard deviations we don't really care about too much, and it's not really highlighted. So what we can really show is basically a bell-shaped curve, the mean, and the standard deviations, and they're giving us this data here conveniently. So we need to mark out 78 on the diagram here, and we'll do that here. So 77, which is here. That's going to be our peak. Now we need to look at our tails. Now, each bell-shaped curve has a tail, and for the lower tail we're going to have to look 3 standard deviations to the left. Now that would be 78, subtract 3 lots of the standard deviation, and we're given the standard deviation as 2, which is equal to 72. So that's going to be roughly where we're going to try and aim for, and around here. And then I'd want to mark out the upper tail, which would be 78 plus 3 standard deviations, which would give us 84. So we're going to mark that here. And then now you just draw a rough bell-shaped curve, and you'd want to touch or thereabouts a peak at 78, like so. That's just a sketch. There isn't much more that you need to do. And then it says label each diagram. This is for French. Now this is going to be 72, this is going to be 84. This is your 3 standard deviations, and you're basically encapsulating the 1 and 2 standard deviations within, so you don't need to sketch that bit. You could illustrate it, but we don't have to do that here. And now we need to look at German. Now German has a higher mean score, 85, compared to the 78, but its standard deviation is higher as well. Standard deviation measures the spread of the data, and it's a good way of measuring how diverse a data set is. Now, if the data is more spread out, it will have a higher standard deviation. Okay, so you might need another piece of information, which is that the area under the curve is pretty much the same. It represents probabilities, and these add up to 1. So the idea is the 2 curves need to have the same area, but the areas are going to be represented differently. Now, because the mean score is 85, it's going to be on this line here, but we need to know where we're going to plot it. We can't exactly plot it exactly in the same peak, because as we can see, the standard deviation is different. The spread of data means that there's more variation in the data set. Hence, we might actually have to reduce the peak of the mean. So we're going to do it somewhere lower, approximately anywhere here would look nice. And then now we can just use our lower tail and upper tail and do the mean plus or minus 3 standard deviations. Now if you put those values into the calculator, 85 plus or minus 3 lots of 2.5, you would get 77.5 and 92.5. I'll start sketching them now. Now you'd want to sketch some sort of curve here, just like the other one. Obviously they do not look nice, but again it's just a sketch. As long as you've shown the bell-shaped curve, you mark down the approximate tails and the values using the 3 standard deviations, and you made the peak of the Germans lower because it shows there's more spread of data, then you should get the 4 marks. Part B. Use the information in the table to make 2 comparisons between the scores in the French test and the scores in the German test, and then interpret your comparisons in context. So first of all, we need to make 2 comparisons, and we just need to use the data, and then we need to interpret those comparisons in context. So when we're doing this, we basically just need to look at what the table's given us, and it's given the mean and the standard deviation. Now the mean generally indicates that German tests had a higher average score than the French, and its highest standard deviation suggests that it's more spread out. That's basically the answer. I'll write that down now. Quick pause, I'm just going to clarify what I've written here. I've written that the test results are generally greater because of the higher mean, and now I'm going to write that the test scores for German are more spread out, and we can see this because of the higher standard deviation, and that's what it means by interpreting the actual comparison, and that's the more spread out and the generally greater scores. One student who took the French test is selected at random. Work out an estimate for the probability that this student scored more than 76 on the French test. So I'm going to have to introduce you to the empirical. Now the empirical rule essentially states all the data must be between 68, 95, or 99.7%, or 99.7% of the data lies within the specific standard deviation. This is for 1 standard deviation, 2 standard deviations, and 3 standard deviations of the data. And you can illustrate this like so. You have your mean here, and then you have 1 standard deviation each side, 2 standard deviations each side, and then 3 standard deviations each side. Obviously this isn't an accurate diagram, but the idea is you cover more and more data with each standard deviation, and the exact values are here. Now you might see slight variations online like 67, and sometimes they might have different values. This is the general one you can use. Just use the one that you see in your notes or on the textbook. So what this relies on is seeing that, well, for the French we had the mean score was 78 and the standard deviation was 2. If you can manipulate those numbers to get 76, you can kind of see that 78 minus 2 gives us 76. Now if 2 is the standard deviation and this is the mean, well, you can kind of look at it. This is the mean minus 1 standard deviation, and if you look at this being the mean, and we're looking kind of at this bit here, everything within this little bar is the mean minus the standard deviation, or 1 standard deviation. Now it's saying to work out an estimate. Again, this will be an estimate, we won't know for sure that this student scored more than 76. Now that's key. If we look at our actual diagram here, where it might be better to illustrate. So for French, it illustrates 78. 76 is here. So if I quickly just draw these dashed lines, this is the mean minus 1 standard deviation. Now we're trying to find the probability it was greater than or equal, or not greater than or equal to, but greater than 76. So therefore we're trying to find everything that is in the pink plus everything that is in the yellow and ignore the overlap. Another key thing that you need to know is that this is kind of split in half. The mean basically represents the middle part of the data, which is a key characteristic of the normal distribution. So 50% of the data lies here, and 50% of the data lies on the other side. So if you look at that key characteristic, you can kind of see that, well, this bit must be 34% and 34%, because if you think about it, this is one standard deviation in total, plus or minus the mean, which gives us our 68. So the probability that the student scored more than 76 is everything to the left of the mean, which is 78, and that's 50%, and everything between 76 and 78, which we've identified as one standard deviation below the mean. Now we know that one standard deviation plus or minus is equal to 68% as per the empirical rule, but because we're just looking at the negative part, we're going to have to divide by 2, which gives us 34%. So therefore the probability is greater than 76 would be equal to 0.34 plus 0.5, which gives us a probability of 0.84 or 84%. Lucy took both the French test and the German test. Before she took these tests, she said that the probability that she will score more than the mean score in both tests is a half multiplied by a half, which is equal to a quarter. Comment on the validity of what Lucy says. If you think back to question 1 before we checked, and independent events. Independent events means that the probability of doing one thing or one event is independent, i.e. it's not affected by doing something else. Now here she's assuming that because 1/2 multiplied by 1/2 gives us our quarter, well, this assumes that it's independent. Now, is it likely to be independent? Well, just think about it for a minute. If you're doing a French test and a German test, well, they're naturally linked together, they're languages. If you're going to do a French test and then a German test, you're probably going to be smart because no one's going to do that by force. So she's likely to score higher on both tests, and this is because she takes 2 languages. So what I would say is that it's unlikely to be valid because it assumes independency. Question 10. A company makes bars of chocolate on a production line in a factory. If a chocolate bar is found to weigh less than 60 grams, the company will not be allowed to sell it. The company uses quality assurance control charts to monitor the weight of chocolate bars. Samples of chocolate bars are taken at regular intervals, and the mean weights of the samples are normally distributed. Explain why it would not be appropriate for the production line to be set so that 60 grams is the target weight. So quite literally, if 60 grams is the target weight and it is normally distributed, so again we're going to introduce our bell-shaped curve. 60 grams is the target, 60 grams the target is always the mean. So the mean is going to be what you're targeting. Now if you target 60 grams as your mean, well, anything less than 60 grams, well, what happens? It's not allowed to be sold. We'll not be allowed to sell it. So would you want to do that? Probably not. So that's the reason you're going to put. If you don't already know by now, 50% of the data is to the left and the right of the mean respectively, because the mean is obviously the median, isn't it? In fact, the production line is set so that the sample mean should be normally distributed with a mean of 62 grams and a standard deviation of 0.4 grams. What can be deduced from this information about the mean and standard deviation of all the chocolate bars made on the production line? So all the chocolate bars made on the production line. I need to refer to this as the population, and the population is again everything you're interested in, and this is all the bars on the production line. And then you've obviously got your sample, which is, well, the subset of data which you select. Now what can we deduce about each of the mean and the standard deviation? 2 marks and 2 rough points that we're going to base it around. So for the mean, look at the 62 grams. What should we deduce from this? Well, you can kind of see that the mean of the population should equal to, or roughly equal to 62 grams, as that's what the normal distribution follows, a mean of 62 grams. So we can deduce from this that the mean of the population should be roughly equal to the mean of the sample, which is 62 grams. So the mark scheme does word it a little bit weirdly, I'll admit, but it kind of makes sense. You're going to try and aim for the mean of 62 grams, but obviously you're not going to hit 62 grams exactly, you're going to have slight variation, hence the standard deviation. Speaking of which, I need to highlight this keyword here, sample means. Now, sample means is when you have a population, and from that population, you take a random subset of data, which is your sample, and you take the average. You do this multiple times to obtain another dataset, which is full of the means of your different samples, and obviously that's where sample means comes from. So the idea of a sample mean is that it's going to be less, but it still will be, but to a lesser extent, it will be less affected by outliers and such, and therefore the standard deviation of the population, which is basically your raw data, will be greater than the standard deviation of your sample means, which of course will now be more closer together because they've been averaged, and that's your second point. Alice takes the samples in order to monitor the sample means of the weights. Here is her incomplete control chart showing 8 sample means. Part C tells us, by completing the control chart, determine what actions, if any, Alice should have taken based on the information given. You must justify your answer. Okay, so the only incomplete information here is that it seems all the sample numbers have been given to us. Sometimes they like to ask us to fill one in and plot it on the graph. However, we don't have to do that here. However, quality assurance isn't particularly difficult. You just need to know some specific things. Now, there's something called action lines and warning lines. It's quite self-explanatory. The action line is when you're actually going to do something, when you're going to act on something, and a warning is perhaps when you're just about to act on something but not quite yet. And this happens at particularly plus or minus 2 standard deviations and plus or minus 3 standard deviations. Now the idea is, if any of the data falls outside 2 standard deviations, then we're going to give a warning. Now, if it falls outside the action limits, the upper and lower limits, then we will actually take action, and in most cases it's stopping the production line. So first of all, let's look at the standard deviation. Standard deviation given to us is 0.4 grams. The mean is given to us as 62. Now we always look at the warning limits first, or I do anyways, so we're going to do plus or minus 2 lots of the standard deviation. For our lower limits, so 62 minus 2 lots of 0.4, we get 61.2. And for our upper limits, so where you have to add the 2 lots of 0.4, we get 62.8. Okay, so now if we look at this, we need to plot this on the graph. So our values are 61.2 and 62.8, so I'll just spend my time plotting them now. That was quite fiddly, however, you should be able to do it with a bit more accuracy. So this would be our upper warning limit, and then our lower warning limit. Now you can see some data already falls outside. So now let's move on to our action limits. We'll need to do 62 plus or minus 3 lots of our standard deviation. So if we type it into the calculator, 62 plus 3 lots of 0.4, or let's do subtract first because we're trying to do our lower limits. We get 60.8. Then if we add, we get 63.2. So now we need to plot those lines, 60.8 and 63.2. So now we need to label these ones, and this will be our upper action limit and the lower action limit. So now, do we need to take any action? Well, we can see that this sample here, sample 7, is outside our warning line, but not outside the action line. And then this sample here, sample 8, is completely out of both the warning and the action line. So we have two samples we need to deal with here, and we need to do them in order, I'd say, makes the most sense. So for sample 7, you should know that when it falls outside the warning limits, but not the action limits, you'd have to take another sample. You'd usually review that and see if it falls outside the warning or action limits. And then for sample 8, well, it's completely above the upper action limit, which is unacceptable. So we just have to stop and reset the machine, which is generally what you mostly do for all the exam questions that you come across. So you get 1 mark from basically labeling your limits, and then another mark from identifying the actual values. So from labeling that you have your plus and minus 2 standard deviations and 3 standard deviations, you get 1 mark, and from actually drawing on the graph, you get another 2 marks. So, and then you'd have to actually state that sample 7 is outside the warning lines. So and then for sample 8, well, it's outside the action. And so your resultant, your last marks are from here. And that is the whole of question 10. A farmer recorded the birth weights in kilograms of a sample of 50 piglets born on his farm. The grouped frequency table gives information about his results. So we'll have our weights here in our class intervals of 1, and actually no, they vary, and our frequencies on the other column. Using the information in the table and the values of W as the class midpoints, the farmer finds an estimate for the mean birth weight of these piglets is 2.29 kilograms. He also finds that the sum of the frequency multiplied by the midpoints squared is equal to 286.875. Show an estimate of the standard deviation of the birth weights of these 50 piglets is 0.7 kilograms, correct to 1 decimal place. Now, standard deviation in general, the sum of x squared over n minus the mean, which is ex over n squared, or sigma x over n squared. Now, for frequency or grouped frequency tables, it's slightly different, and you don't get given this formula. However, you do get given this formula here for the normal standard deviation, so you're not completely in the dark, and you can just learn that it's going to be the frequency just gets slotted next to the x. So the frequency multiplied by x squared over n minus the sum of the frequencies times x over n, and then square that. And they've kindly given this value here with 2.29, and they've given us sum of f of x squared, which is this one right here, and it's 286.875. We know that n is the number of values and that there are 50 piglets, so that's quite self-explanatory. So from here it's just a matter of plug and go. So I'm just going to substitute the values in. The sum of f of fx squared, or fw squared as it is in the question, is 286.875 over n, which is 50. And we don't have to do the mean, thankfully, so less workings for us. So just 2.29 squared. If you type this into your calculator, you get 0.7024 and so on kilograms. And then to one decimal place, we just have to round this and we get 0.7 kilograms. And that's your answer right there. So this one wasn't actually as hard as it looked. You just had to know the formula, which again is kind of given to you in the formula booklet. You just need to remember, you need to put the frequency next to the x, and then from there it's just picking out the information and plugging it in, and not too much difficulty here. But then it was only 2 marks. Calculate an estimate for the skew of the birth weights of the piglets. Go to your formula booklet and you'll know that the skew is equal to 3 lots of the mean minus the median divided by the mode. Standard deviation, sorry. Look to our question here where we're given all of our data. We've got the mean here. We've got the standard deviation now to one decimal place. What do we not have? Well, we haven't got the median. So we're going to have to find that now. Now the median has a formula, and I can put it here. It's basically the start of the class width plus the remainder or something like that. I can't tell you the definition or the official formula because I haven't got it on me. You can learn this if you want. However, a more easier way to do it is just using intuition. The only way you'll be able to do this in the pressure is when you need to understand what it's actually asking for. Now, the median is just the middle point of the data. The sum of the frequencies is 50, and if you look for the median will be 50 over 2, or the 25th value. That's all it's asking us for. Where is the 25th value? Now, if you did a cumulative frequency, you'd kind of see that we have 4 here, 16 here, and then if you add 17, you'd have 33. So the 25 is somewhere within this category, the 2 and 25. Now the question is, how far into it is it? And because we're going to estimate the median, what value could we give it? So if we go back to this, it starts at the interval 2, because that's the minimum value in that interval. In terms of the class intervals, the cumulative frequency was 17 and then 33. We needed to work out where 25 went in. Now 25 is an addition of 9 out of a class width of 16, if I'm correct. Was it 16? No, it was 17. I've got the values the wrong way round. So we need to add 9 out of 17, and we need to multiply it by how large the class interval is, which is 0.5. And this gives us a value of 2.2647 and so on. And we'll just round it to 2.26, which is 3 significant figures. Now we just need to plug the values in. So the skew is equal to 3 lots of the mean, 2.29, minus the median, over the standard deviation, which is equal to, if you type this into the calculator, 0.1285 and so on, which are round to 0.13. Now they give a range for this, which is why I wouldn't worry about what you round your median to, but it's 0.1 to 0.13 if you're wondering in the mark scheme. if you're a bit confused by the median, well, I wasn't able to quite so much explain it in detail, and I probably wouldn't. I don't think it was a good explanation anyways. However, be sure to revise that. In a nutshell, this is your class interval, the minimum. We're looking how far you went into that class interval in terms of the frequencies in order to get to the median, and then we multiplied it by the class width. I know that wasn't a good explanation, but hopefully it still makes sense if you do know how to do it. If you don't know how to do it, please revise it and then come back, and then hopefully it should make sense. Part C asks us to interpret our answer to Part B. The key word is interpret. It wants you to find the value or explain it, and then you need to give context. So 0.13 indicates a slight positive skew. Now if I illustrate this using a positive skew diagram, which should look something like so, if the median was located here, then you can see that more data is packed in this part here, but there's more spread to the right of the mean. So we could say that the weights above the median have a greater spread than below the median, as you can see illustrated by the graph. Part D. Using only the information given in this question, explain whether it is possible to deduce that any of the birth weights are outliers. Justify your answer. Now, outlier limits are anything plus or minus 3 standard deviations. Now, if we look at this, we need to do the mean, which is 2.29 as given per the question, and then we need to plus and minus the standard deviation, which we find to be 3 lots of 0.7. Put this into your calculator and you'll get two values. You'll get 0.2 and 4.4, which are rounded values. Now, we need to look at these values in detail. So we have 0.2 and 4.4, so remember those. Now the smallest value starts at 0.5. It's impossible to have any values less than 0.5, hence we can't have a value 0.2 because, well, there's no class interval for it. So that's impossible. Now 4.4. 4.4 could well be in here. It's possible, but we don't know exactly. Because for all we know, all the data could be 4, 4.1, 4.2, and none of them actually eclipse 4.4. However, we could also tell that some of the data could be 5.8, 5.9, which in this case would be an outlier. So all we can say is we don't know for sure, but it's possible there are outliers. And that is the end of the paper. So please do give me feedback on how I've been. I do appreciate critical feedback as well, so if there's anything that you want me to change, please be honest, and I'd rather make changes than keep the same format and just do it terribly. And also, if you appreciate it, let me know as well in the comments, because it keeps me going and motivated. And if you want a paper too, do let me know. And yeah, thanks for watching.